Hello and welcome, coming to you not quite live from One Take Studios, where today we are talking about operations with functions. Operations here does not include having a kidney removed. We are talking the basics. We are talking adding, subtracting, multiplying, and dividing. Those are our operations. I am going to also discuss compositions at the end of this video if you're curious about that one. Alright, so a lot of this your brain actually knows. You just have to trust it a little bit. So go with your gut, which is your brain, basically at the same time. Alright, so I'm going to start with a function bank. This is just basically a group of functions that I've got that I'm going to draw from to be able to do my examples. So this first one, function bank, f of x is equal to 4x squared plus 3x minus 1. And for my second one, g of x equals 6x plus 2. What can I do with these things? I can grab my bottle of water. That's what I can do. Okay. First up, first example, what do you think that looks like? What do you think it's asking? Two functions. This is sort of like function notation. I can see the f plus g. I'm pretty sure this is asking me to take my two functions, f and g, and add them together. So what do you think I'm going to do? Add them together. I've got the 4x squared plus 3x minus 1. I'm going to add to that the 6x plus 2. This is just adding like terms. You've done this a bunch of times. Alright, so be brave, put things together. Equals, that's going to be 4x squared plus 3x plus 6, so plus 9x, minus 1 plus 2, that's going to be plus 1. Congratulations, that's it, that's all. Ta-da! We have added functions. Biggest thing with this that you want to watch out for is some people think this is f plus g times x. Again, know that you're working with functions, know that this is function notation, and that will really help. If we add, can we subtract? Dun dun dun! I bet you we can. So again, I can see the f minus g. It's asking me to take my two functions and subtract them. So I'm going to do exactly that. Again, the f comes first. That's the first function I'm going to write. 4x squared plus 3x minus 1. If you're going to mess something up between addition and subtraction, you're usually going to mess up the subtraction. Why? Because you're subtracting everything in the second function. I'm going to put an extra set of parentheses here for my 6x plus 2, so that we can see that I'm not only subtracting the 6x, but I'm also subtracting the 2. I'm subtracting the entire second function. If you would like to put both polynomials in parentheses, you can do that. That's fine. It doesn't mean that we're multiplying. We still have a subtraction sign. We're just subtracting. So equals, like terms, 4x squared, that's the only one of those, plus 3x minus 6x, that's going to be a minus 3x, and then careful, careful, minus 1 minus 2 for a grand total of minus 3. That's it. Alright, so really adding, subtracting, no big deal. We're not going to worry about that one. That one's not super crazy. What would this mean for multiplying? Alright, I've got another function bank for us here. This one, our functions are going to be f of x equals 6x squared minus x minus 12, and the second one is g of x equals 2x minus 3. So we're going to pull from that function bank for our next example here. What does this look like? Well, we know this is function notation, so this is f times g of x. This is asking us to multiply our functions together. Messy, but true. This time I absolutely want to use parentheses around my polynomials. So 6x squared minus x minus 12 times 2x minus 3. There's nothing between there because this is multiplication. I want this one times this one. How does this work? Well, basically, this works like the distributive property on steroids. Alright, so we're talking the 6x squared times the 2x and the 6x squared times the minus 3. So I'm going to start there. 6x squared times 2x is going to be 12x cubed. And 6x squared times minus 3, that's going to be a minus 18x squared. Keep going. Next term, the minus x. This guy, minus x, is going to be times 2x and times minus 3. So negative x times 2x is going to be minus 2x squared, and negative x times negative 3 is a positive 3x. Am I going to fit? Hopefully it'll make it here. The negative 12 is up next. Negative 12 times 2x, negative 12x times negative 3. That's going to give me a negative 24x, and then plus 36. All that's left is to fix up our cleanup on aisle 12 here. We've got like terms. Let's put them together. 12x cubed, great. I've got an x squared and an x squared minus minus, that's going to be minus 20x squared, plus 3x minus 24, so let's call that a minus 21x, and then plus 36. Is it slightly tedious? Yes. Do you have to be careful? Yes. Will you survive? Yes. All right. This is not a huge deal, but you do have to focus. All right. So just pay attention and knock it out. You got this. All right. So if we can multiply, can we divide? What would dividing look like for this? Well, all right. So notice how it's got the f over g. So that's how we know it's division. And the way that this is set up, we're actually going to set ours up the same thing. We're going to go with the function f on top, the function g on the bottom. So 6x squared minus x minus 12, and that's going to be over 2x minus 3. Wait a minute, how do I divide? I know how to add, subtract, and multiply. What am I supposed to do with this? Well, have you considered factor and cancel? Basically, we have a fraction, we just would like to simplify that fraction a little bit. So what would that look like? Let's see. 6x squared minus, I'll bet you 2x minus 3 is one of my factors for the top. What would that mean? That means this would have to be 3x, because 2x times 3x is 6x squared, and this would have to be a plus 4, because that's on the end there. Why did I choose 2x minus 3? Because it's in my denominator, and I have a sneaky suspicion that that's going to work. So check that out. Let's check the OI for the FOIL. We check the first, we check the last. Outer, 8x. Inner, minus 9x. 8x minus 9x, ding, 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 there we go. Those are the proper factors. Over 2x minus 3. Convenient, I say, convenient indeed, because factor and cancel, gone. So all that's left is we are just saying that this is going to be 3x plus 4. Will you always be able to factor and cancel? No, probably not. But if you can simplify, this is going to be one way to do it. I suppose if you really were interested, you could probably get into some long division or maybe even synthetic division stuff, depending on what you got going on here. Some of these can get pretty messy. All right, now, what do we have to consider that we haven't considered yet? This last one, is it undefined anywhere? And why did I not bring this up earlier? Well, what does this have that the last three don't have? Fractions. Oh, and what am I not allowed to divide by? 0. Oh, so even though my answer is 3x plus 4, and 3x plus 4 is not a fraction, I need to not only look at my outcome, but I need to look at all the all the polynomials that I used the whole way through, and check out any denominators I might have. Looking at this, I know that x cannot possibly equal 3 halves, because if x were to equal 3 halves, we would divide by 0, and the world would end. Okay, maybe it's a little dramatic, but that's what we're looking for undefined stuff. So let's put the spotlight on undefined stuff for a moment here, shall we? All right, so first of all, what I just said was, if we are looking for where it's undefined, you want to look at all of the functions, everything throughout the entire problem, beginning to end, not just the final outcome. Check for anywhere that it could possibly be undefined. Also, just now we looked to see where there are zeros in the denominator, because we cannot have zeros in the denominator, and so that's going to be someplace where it might possibly be undefined. I added another bullet point here because it's not going to come up today, but it is something that comes up as well. What else can I not do? Well, as long as we're sticking in the world of real numbers, I cannot divide. I cannot take the square root of a negative. Now notice I didn't write square root. I said no negatives under an even radical. In other words, I can't take the square root of a negative. I can't take the fourth root of a negative. I can't take the sixth root of a negative. I can take the third root of negative, so if I've got an odd radical, that's okay. But any even radicals, we cannot have negative values there, and so that's going to be another thing that ultimately you want to look for when you're looking for undefined functions, or places where functions are undefined. All right, another function bank. Why? Because, as promised, we did adding, subtracting, multiplying, dividing. Now let's look at compositions, shall we? All right, so this is not like English. We're not writing any essays here. Thank you, Jesus. What does this mean? Well, what is that? What is that? What is that? All right, well, all right. Give us some space to work here. What is this? And how is this different from multiplication? Because please note, finding my paper, this paper right here, please note that multiplication looked like this, where I'm saying I'm doing the f times the g of x. this does not say the same thing. This says f of g of x. Notice where the parentheses are. They do not say the same thing. This one says multiplication. This one says composition. Okay, how does this work? Well, notice that this function g of x is on the inside of this whole overall mess. What that means is I want to take function g of x and I want to plug that into function f. It's just like if this was f of 4, I would plug in the number 4. Well, this is f of g of x, so I'm going to plug in the function g of x. So what this really is a substitution. Substitution, because I can spell. There we go. All right, so compositions are really just substitutions. And let's see if we can make this happen, shall we? All right, so we have the function f of x. And normally, I'm going to erase something here, so you might not want to write this down just yet. Normally, this function says x squared minus 1. That's what f of x is, x squared minus 1. But this says, in place of the x, in other words, I'm going to remove this x, and in place of this x, I'm going to put this entire function. Ooh, that's a little weird. Because that's going to be this instead, x over 1 minus x. And that means I'm going to make my square a little bit higher, too, to make it a little bit more appropriate. There we go. That's it right there. So this is f of g of x. I took g of x, which is x over 1 minus x, and I plugged it into the other function in place of the x. I did not multiply them together. I plugged one function into the other function. Can I make your life miserable just momentarily? Can we simplify this? Because that would mean we're subtracting and that one's a fraction, and I bet we can do this though. I bet we can make this happen. So equals, this one is going to be x squared over 1 minus x squared. Alright, so properties of exponents say we're squaring the top and the bottom because it's division. Minus 1. Well, how do I turn a 1 into something useful? Well, it would need to have the same denominator as this one. This one has a denominator of 1 minus x squared, quantity squared. So I'm going to multiply this one on the top by 1 minus x, quantity squared, and on the bottom by 1 minus x, quantity squared. If I multiply that times my 1 that's here, I'm going to have the same denominator. I'm going to be able to put these together. Messy, but true. What does that mean for my numerator? The first one was an x squared. It's good to go. It's got the proper denominator. Leave it alone. The second one now has the proper denominator, but I do want to actually FOIL out my numerator so that I can combine my like terms, because remember, I'm subtracting the second part here. So what happens if I actually FOIL 1 minus x quantity squared? You weren't going to distribute that square, were you? You better not. No. All right, so that's going to be a 1 minus 2x's plus x squared. There we go. That is the outcome of our FOILing. And that's going to be over our common denominator of 1 minus x squared. So last thing to do, just combine a couple like terms here. Watch our signs. Be careful with the signs. Notice this is x squared minus x squared. Oh, that means my x squareds just canceled out. What else do I have? I've got a minus 1 and a minus negative 2. That means I've got a positive 2x and a minus 1. That is my new numerator. Over 1 minus x, quantity squared, that is my denominator. So the idea of a composition is just to do a substitution, but then sometimes the cleanup, if you're asked to do the cleanup on this, can get kind of messy to simplify. Alright, so just kind of keep your eyes on what you're doing, and remember all of your work with rational stuff, because, ooh, fractions, exciting. Is this going to be undefined anywhere? What do you think? Beginning to end, looking. We've got no radicals, so we don't have to worry about this guy right here. Is it possible that we could have zeros in our denominator? It is. So, what can x not be? So let's phrase this in terms of domain, shall we? The domain for this function are going to be the set of x's such that x cannot be 1. Because if I had x is 1, minus 1 is 0, and the world ends. There we go. There's our domain for our function right there. Okay, just one last thing I think that I would like to point out. Please understand that the order of these makes a difference. G of f of x does not create the same composition as f of g of x. So please pay attention to the order of these. Whichever one is in the inside, that one is being substituted into the outer function. All right, so the inner function substitutes into the outer function. Keep your eyes peeled, okay? Have fun.